So last time we talked about quantum probability 101, if you will, by recalling classical probability 101 and making a bunch of analogous definitions. And we're going to do the same thing today with quantum information theory, a kind of a speed run, one lecture on the basics of quantum information theory by analogy with classical information theory. And we'll see by the end of it an important theorem called Holevos bound in quantum information theory. OK, so quantum information theory started and kind of, not ended, but I mean, it was all done basically in one paper by Shannon in 1949. And as before, let's go to just definition one. What is the most basic definition in information theory? And it's this. It's a definition I hope you're familiar with, you've seen before. So if you have a probability distribution P with D outcomes, like before, a probability distribution on the numbers 1 through D, then there's a numerical quantity associated to it called its entropy, denoted H of P, which is this thing, sum of pi log 1 over pi. Again, I hope you've seen it before. So one intuition for this quantity, and the one that I'll maybe refer to a couple times today, is like imagine you're writing a computer program that's supposed to generate draws from P. Okay? And of course, it needs its own like random coins of some sort. Well, imagine the only thing that it gets is like just purely random coin flips. And the entropy kind of measures how many truly random bits or coin flips you need on average to simulate one draw from P. And that's not exactly right because of things like not every fraction is a power of a half. But this is like literally true if you're also consider like amortizing the number of coin flips used over the generation of many independent draws from P. There's another intuition which is like comes from data compression. Like if you needed a scheme for like storing the outcome of one draw from P, on like a hard drive or something, such that you could recover the draw. What's the least number of bits on average you could use with the best compression scheme? And you can even imagine how you could see how these two things are related, right? Like if you had like a good scheme for generating draws from P's, right? Then like your compression scheme could just be, for a given outcome, to write down the truly random coin flips that lead to that output. So anyway, here's like an example where it comes up exactly right, because luckily these are all powers of 2. If D is 3 and you have half probability of 1, a quarter probability of 2, a quarter probability of 3, well, you can plug it into this formula. You'll indeed get 1.5. But to match this intuition, I mean, like the best way to generate this with truly random bits is flip a coin. If it comes up heads, then you can output 1. Otherwise, flip another coin to decide whether you should output 2 or 3. And on the average, you'll use 1.5 coin flips. OK, so a couple more basic facts about entropy. It's a number, and it's always non-negative. And I mean, so it's kind of clear based on this. And when is it equal to 0? Somebody probably can tell me. Yes?
When you just have 1, 0, 0, 0.
Yeah, if P is like deterministic. So if like Pi equals 1 for some I. And so the draw from P is just always outputs I, so you don't need any coins to generate that. It's kind of a pure probability distribution. And the maximum can be is log base 2 of D. We put log base 2 because it's nice to measure things in bits. And when do we have equality here? There's one. Yeah, when it's the uniform distribution. And then all these log base 2 of 1 over pi's will be log D, and it'll add up to log D. And if D is a power of 2, it exactly matches this. But anyway, this is the intuition. This is the exact formula. OK, great. So, well, now we do the quantum information theory definition 101. I guess I'll put it over here. And it's the same definition. But we want to have the entropy of a quantum random source. In other words, a mixed state. So this notion was introduced by von Neumann. So it's called the von Neumann entropy. Actually, I'm just thinking, historically, he probably invented it before Shannon, right? Probably in like the 20s or 30s max.
Shannon asked von Neumann what to call his thing, and von Neumann said entropy because
yeah, if you call it.
Always win an argument.
Yeah, because nobody will know what exactly entropy means. So if you call your quantity entropy, then yeah, exactly. So that's funny. So this is definition 0. That pathetic thing is definition 1. OK, so the von Neumann entropy of a mixed state, a D outcome mixed state, or density matrix, rho is, well, I'm going to denote it by h sub rho. So I'm kind of overloading h here. Some people do that. Maybe it's mildly more common to use capital S, which somehow maybe stands for entropy in German or something. I'm not sure. But I'm going to just call it h, and you'll get the difference if I'm talking about quantum or classical. So it's also a number based on rho, which kind of measures how random or uncertain rho is. And you have to be a little bit careful here. I mean, if you treat of it as like kind of a measure of uncertainty, there's many different mixed states that all have the same density matrix. But the right thing to do is to take like the or a canonical one, where I'll put a dot 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 here and say like if rho has eigenvalues lambda 1 through lambda d. As we saw in the last couple of lectures, if rho is a density matrix, it's Hermitian, it has these eigenvalues or stretching factors, and density matrices have the property that these are non-negative numbers adding up to 1. So they form a probability distribution, and they each have associated vectors in an orthonormal basis. And so it's kind of like the canonical density or mixed state for a density matrix, the one where you have the orthonormal basis, pure states with these as their probabilities. So you should take this as the canonical mixed state, and therefore you should define the von Neumann entry to be this sum I goes from 1 to d of lambda I log base 2 1 over lambda I. Okay, so this is the entropy, the classical entropy of like a probability distribution, namely the one given by the eigenvalues of rho. Okay, so particular does not depend on the eigenvectors of rho. And somehow it represents the amount of uncertainty about which pure state rho is in this canonical mixed state. So let me make a little quiz for you here. There's the definition. Let's do an example. OK, so quiz. So here's the qubit. Let's go back all the way to lecture 3 or something. The qubit, which we like to call plus. This is a d equals 2 example. It's 1 over root 2, 0, plus 1 over root 2, 1. Well, now we like to write everything in terms of density matrices. So it has density matrix can somebody tell me what is the density matrix for this? Yeah?
All 1/2.
That's right, yeah. It's a half, a half, a half, a half. Remember, because it's 1 over root 2, 1 over root 2. In bra form, times 1 over root 2, 1 over root 2. OK. I'll call that rho. So what is the entropy of rho? Von Neumann entropy. Can somebody tell me? Sure.
0.
Very good. It's 0. Zero because, first of all, it's always going to, yeah?
I think it's 0 because one of its eigenvectors is just 1, and that has the eigenvalue 1.
One of its eigenvectors values is 1, and the associated eigenvector is plus, and the other eigenvalue is 0, and the associated eigenvector is something orthogonal to plus, which would be minus. That's right. So pure states always have entropy 0. Because, if you think of the associated density matrix, if it's a pure state psi, the density matrix rho is, 1 times psi, psi, plus, well, nothing. Okay? So a pure state, the lambdas for it look like this. There's a single 1, and the rest are zeros. OK, so you might have thought that, like if you measure this, you get like 0 or 1 with different probabilities. But no, pure states have 0 von Neumann entropy. OK, so in fact, let me make a little intuition for this von Neumann entropy that's sort of analogous to that intuition. And or an interpretation. So H rho is like the least number of coin flips you'd need on average to simulate, like the outcomes. Let me write the random outcomes of, let me write it like this, your favorite, i.e. the cheapest, measurement in an orthonormal basis. Okay, so if you have some density matrix rho, consider all the ways you could measure it in an orthonormal basis. And imagine that whenever you choose one, you then have to write a computer program that generates the randomness needed to say the outcome of the measurement. And you're going to pay the number of bits needed on average to generate those. So you're going to pick the best, cheapest one and measure on that basis. And what you should do is pick the orthonormal basis of eigenvectors for rho, and then you'll get this distribution, and you'll pay the entropy of this classical distribution. Okay, so for in particular, for this qubit, a bad idea would be to choose the standard basis. If you measure this qubit in the standard basis, then you'll see 0 with probability of half and 1 with probability of half, and so that's like a coin flip. You'll have to pay 1. But the smart thing to do is measure it in the basis of plus and minus. And then you'll see the outcome plus with 100% probability and minus with 0 probability. And you'll need 0 coin flips to simulate that. OK? Yeah?
Why that orthonormal basis is the best?
I guess it requires a proof.
Oh,
Yeah.
okay. No.
I don't see immediately why, but yeah. Yeah, I'll try to think of a short proof. Actually, so let me compare this situation to the maximally mixed state. Let me say the maximally mixed qubit state. Which in sort of mixed state form, one way to write it is 50% chance of 0, 50% chance of 1. Of course, this is not the same as this. This is a pure state. This is a mixed state. Do people remember the density matrix for this state?
Just 1/2 on the diagonal and zeros otherwise. Yeah.
Right, 1/2 on the diagonal and zeros otherwise. It's a half times the identity matrix. And this thing actually has the property that for any orthonormal basis you measure it in, anyone at all, you'll get 50% probability of each of the two outcomes. Because it's actually equivalent to 50% probability of some u and 50% probability of the perpendicular u. OK, so no matter what you do, you're going to have to pay 1 bit of entropy. And indeed, the maximally mixed state, in general, I mean, these are its eigenvalues, so it has entropy 1. So great. Luckily, I haven't erased this yet. So let's just turn this into a curve EP. So it's a rho. And this fact remains true, right? Because, I mean, this is always the entropy of some actual probability distribution, depending on rho, the eigenvalue distribution. OK, so it can be as small as 0. And we see it's with equality if and only if this holds for the lambdas. And that's the same as saying rho is pure. OK, so the von Neumann entropy of a density matrix or mixed state is 0 if and only if rho is pure. And on the other hand, we have equality here if and only if the vector of eigenvalues, lambda, looks like all 1/d's. And I think as we saw last time, I mean, that basically means it stretches by a factor of 1/d in every direction in space. So it has to be 1/d times the identity matrix. In other words, the maximally mixed state.
particular row should actually be equal to 1 over d times the identity, right?
Yes.
Yeah, there could not be any other.
Yeah, there's nothing else, yeah. Okay, so that's it. Any other questions? That's definition number 1, quantum information theory. Okay, good. So now things really only get fun in information theory when there's 2 people involved. Alice and Bob, you're communicating, you're talking about mutual information, stuff like that. We'll get to that in a second, but actually, in order to get that, we have to do one more kind of quantum probability 101 thing. So let's do that first. As always, we'll start with classical probability 101 with 2 people involved. So this is a reminder of something that you know. Let's say x and y are random variables, each taking value between 1 and d, like we like. So I'll say let me use this notation, square brackets d to be the integers from 1 up to d. But let me emphasize that they're not necessarily independent. So they have a joint distribution. Joint probability distribution, which we'll write as P, which is on d cross d. Okay, so it's a list of probabilities for each pair of numbers between 1 and d that add up to 1. And let me squeeze it on here, a running example. Okay, so I'm going to do a little running example here. Imagine d is 4. Okay, so x and y are both numbers between 1 and 4. And I want x and y to be basically uniformly random, but subject to one condition, subject to x plus y is even. Okay, there's nothing like super interesting about this, but it's just an example. So in particular, another way to put it is they're uniformly chosen, the pair x comma y is uniformly chosen from the set. I'll just start listing out all the pairs that work. So you can have 1 and 1, you can have 1, 3, you can have 2, 2, you can have 2, 4, and there's 4 more, the last one being 4, 4. Okay, is it clear? So in particular, for this particular p, p of 1, 1 is an 8th, and p of 1, 2 is 0, okay, etc. P of 4, 4 is 1/8. Okay? And as in quantum, we'll imagine that somehow like Alice holds x and Bob holds y. Okay? Alice is hanging on to x, Bob's hanging on to y. And I'm saying all this just to define the notion of the marginals of p. If you know that term, we just want to ask, what is the distribution of what Alice has, just x. It's some probability distribution, which I'll call P sub A for Alice, on 4 outcomes, 1, 2, 3, 4. And in general, it's called, Alice's marginal distribution. Okay, and similarly, P sub B is the marginal distribution on what Bob has, the distribution of y in isolation. Okay, in our example, in fact, PA is the uniform distribution, and so is PB. Okay, if you make a draw from this and then just forget about y, you're equally likely that x is 1, 2, 3, or 4. But of course, as in quantum and entanglement and so forth, right? I mean, it's not like the overall distribution P is the uniform distribution on all 16 possibilities. They have a joint distribution. And if you want, you can write down like a formula for the marginalization in general, like the probability on Alice's side of an outcome x is, the sum over all y's of the joint distribution Pxy. Okay, and similarly, you can write a formula for PB. Okay, hopefully that's familiar sounding. So now I want to do the quantum case of this. And it's something we've actually already talked about before, but I just kind of want to emphasize it. It's just the fact that, Alice and Bob can both be holding on to some d-dimensional particle. There's two d-dimensional particles, but these are entangled. So there's like a joint state that they have. But you can also just try to ask, like, what is the state by itself of each of the two particles individually? And now we can really talk about this properly once we have the notion of mixed states. We couldn't really talk about it properly when we only talked about pure states, because even if the joint distribution is pure, Alice's view of the situation is always a mixed state. Let me just go over that a little bit. OK, so the story is Alice and Bob both have a qubit particle. So there's two particles, each d-dimensional, and they're possibly entangled. OK, so the joint state, the two particles together are a d² dimensional system. So the joint state is d² dimensional. And now, it can be a mixed state too, potentially. So it's some rho. That's d² by d². OK, and just like we had a running example here, let's pick the nicest running example, which is an Epr pair. OK, remember, this is the pure state, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1, which is 4-dimensional. Because here d is 2. They both have a qubit. So we're imagining the joint state happens to be pure in this example. But OK, we should always write it as a density matrix. OK, so in that case, it's this guy times the row version of this guy, which looks like this. It's not too important, but I'll write it down anyway. OK, but now we want to ask this question, what is the state of, and it's always a mixed state, of Alice's, qubit alone. And now that we're talking about pure mixed states, we can talk about this. I mean, the thing you should imagine is, Bob will never be seen from again. Alice is just going to start doing some experiments with her particle. And all the future measurement outcomes can be explained in terms of just one state, rho A, a d-dimensional state for Alice's particle. But even if the joint state is a pure state, this state will be a mixed state. And what is it? Well, as we've described before, let's say the joint state is a pure state. Then it's just the mixed state that you would get if you imagine that Bob measured his half. Because if he's over on Jupiter, for all you know, maybe he did measure his half. Okay? And so then we know the rules of how you take a pure state that has two parts or multiple parts, and you do a partial measurement on one part. It gives you a probability distribution over what the Alice part collapses to. And that's a mixed state, probability distribution over pure states. So Alice's rho A is a mixed state. It's just whatever you'd get if Bob measured. And you might say, oh, but what if they started with a joint mixed state? That's fine. A mixed state, you can just think of it as a probability distribution over pure states. And so you can still understand what Alice would see if Bob would measure. There'd just be this additional layer of classical randomness on top. First, according to the rho, you have a probability distribution over the big pure states. Bob measures. That makes further probability over the pure state that Alice's state collapses to. So a mixture of mixtures is still a mixture. And so I'm just trying to convince you that you know all the quantum rules you need to know in order to figure out what rho A is as a function of rho. OK, so for example, in the example, we've done this example several times. When rho is the Epr pair, rho A Well, it collapses 50% of the time to 0 and 50% of the time to 1, which, well, we saw it just a minute ago, is the maximally mixed state. And in this case, rho b is also the same. It's symmetrical. But of course, I mean, I'll give you this reminder. Hopefully it's clear. It's not the case that rho necessarily is rho a tensor rho b. Okay, just like it's the case here, it's not like the overall probability distribution is the independent draws from these two things. Okay, so this is an operation. There's an operation, it's called marginalization here. We could call it the same thing here. The operation that takes rho and produces rho A, in particular, it would take this matrix and produce this matrix. You could call it, I'll call it quantum marginalization. I don't know how many people use this phrase, but why not? The phrase that they do use a lot is partial trace. So I'm saying this because you may encounter it in your life. This operation is called the partial trace, over the bob part, the B register. And it's written trace sub B. And sometimes it's called tracing out the bob part. And similarly, the quantum marginalization that takes rho to rho B is it's called tracing out over A. But yeah, that's it. I mean, never mind. So sometimes people will write an extremely nasty formula for how you compute this matrix from this matrix. It's somehow like a partial trace. And one way, I think you look at it as a block matrix, and you take the trace on each block, and that's how you get one of the two, and then you block it in a different way and take the trace, and you get the other one. But I prefer not to remember that. I just prefer to remember if you want to know what rho A is, it's just what you'd get if you applied the measurement rules of measuring the B part. Okay. Any questions about that? Okay. Good. So let's get back to information theory. As I said, things start to get fun when you have two random variables. Right. So let me keep this. So again, let's imagine we have two random variables, x and y, each taking values between 1 and d, and they have some joint distribution p. Okay, so it might be this example again. So now I want to think about the entropies of three different things. I want to think about the entropy of x, the entropy of y, and the entropy of the joint random variable x comma y. Okay, so h of pa, let's do this example. Remember where x and y are uniform between 1 and 4, but subject to that they add up to an even number. So what is h of the marginal distribution pa?
Two.
Should I take the average? 1.5? It's 2. Right? What is the distribution PA? It's the uniform distribution on 1 through 4. All right? If you draw uniformly from this set of size A and just squint and only look at x, you see a random number between 1 and 4. You need 2 coin flips to generate that, a random number between 1 and 4. So the entropy is 2. Okay. Entropy of PB is 2. Yeah, it's the same. Okay, and now what about entropy of P? Which is asking, okay, now if you want to generate this distribution, how many coin flips do you need? You want to generate the pair.
3.
3, that's right. Do you want to describe one way in which you can do it? Yeah?
It's 8-dimensional because there are 8 possibilities.
Yeah, it's actually the uniform distribution over 8 different objects. So you can generate it by just flipping 3 coins, getting a random number between 1 and 8, and outputting, the whichever one of these. let me write it in a funny, different way. Here's like another way you could do it.
Oh, you want an algorithm?
Yeah. Yeah.
You can first, I think you can first flip a coin to generate like the sum of these two.
The actual sum or the sum mod 2?
Well, I was thinking about the actual sum. Yeah, you can do sum mod 2.
Yeah, the sum has a funny distribution. I mean, I'm not quite sure what it is. I was going to do that, right? So, I mean, you can also just, as you know, said, just flip 3 coins that generates a random number between 1 and 8 and pick the ith one here if you generate I. But here's another way. Flip 1 coin to decide if you're going to do odd odd or even even. And if you look at the possibilities, indeed, like half of them are odd odd and half of them are even even. OK, and then once you do that, let's say you've decided it's going to be odd odd, then basically, x is either 1 or 3, y is 1 or 3, and they're independent. I mean, you can just independently flip a coin for, finish x and y with 1 coin flip each. Right? Or if you decide it's going to be even, then you just have to pick x to be 2 or 4 and y to be 2 or 4, and there's no additional constraints. So you needed 1, 2, 3 coins. This is a different way to do it. But I wrote it this way because it slightly motivates the following definition of the mutual information between x and y. Okay, so this is like definition number 2 in classical information theory. The so-called mutual information of, I guess, P, the joint distribution. So it's probably best to write it like I of P or like I of PA, PB, although it's honestly usually written the joint information between x and y. So these are all notations for the same thing. But here's the formula. It's entropy of A, of PA, plus entropy of PB minus entropy of P. OK, so let me interpret this for you. Imagine you had to write a computer program to generate these pairs x and y, these joint distributions x and y. OK, the naive thing to do would be like, well, first, if I had to generate x and y separately, like I had to make a draw from the marginal distribution of x and also a draw from the marginal distribution of y, that would cost me this many bits plus this many bits. But when I draw them together, it only costs this many bits. So the interpretation of this is the savings you get by virtue of generating them together versus if you had to separately generate a draw from x and a draw from y. Okay, so you should really think of this as like the savings when, or from generating x and y jointly. Again, this is like intuition, and you can make it more precise. And if you don't want to work at this fuzzy level of savings and so forth, then you can just rely on this formula, which in turn has a formula involving logs and stuff. But this is how you should think about it. And let's just illustrate it here with this example. So in this example, well, let's first just write the formula. So the mutual information between x and y is entropy of the x, which is 2, plus entropy of y, which is 2, minus the entropy of the joint random variable, which is 3. So it's 1. Okay, so the mutual information in this little example between x and y is 1. And I feel that this story kind of illustrates that in the sense that this one coin to decide whether it was odd, odd, or even, even was kind of like the one mutual information bit between them. That was like the one bit that you jointly used. And sort of conditioned on that, they became independent. So you had to do the rest of it separately. Yeah?
So, okay, it's a very vague question, but from what you described before, what I imagine is kind of, you can have an algorithm that generates x and y separately.
Yeah.
And if x, y kind of bad, say that it sums up to odd, you just discard that pair. And the mutual information actually measures that discard as a saving. And this is different from like actual one. So you see, it's like complement. Like, is that right or not?
Somehow think of it a bit more like, you know, the actual cost in random bits to generate p jointly is h of p.
Yeah.
And this is a bigger number.
Yeah.
I mean, it's
Okay, let me put
yeah.
this. So it feels for me that this one stands more for discarding odd even and even odd at the first coin flip, rather than picking odd odd and even even. And it just happens that they're equal in this case. Is that?
Let me think about that.
I guess there is a sense in which you're right, because you have to.
Who's right,
things.
Alex or me?
I mean, because you have to discard things, right? So it generates inefficiency in your bits, right? So the natural thing to ask is, you know, what's the most efficient way to do it? So yeah.
The story I kind of have in my mind, I mean, this is a picture you'll see drawn, although it's even like less accurate. It's like somehow this is x and y, and like this is like h of x and h of y, and like this is like the mutual information. Kind of like the overlap. It's kind of like you first kind of generate the common part using mutual information many bits. And then like to generate the rest of x and y, you do it separately or independently. There's another interpretation, which let me mention.
Oh, wait.
I'll write another interpretation and see if you like that.
Okay.
It's like a Venn diagram, right? Like this is h of x plus h of y. Then you take away the intersection. Wait, sorry. What?
Yeah, that makes sense.
Yeah.
That's what I was
Okay,
confused about.
got it. Okay, yeah, I also just confused myself. Okay, good. So like another interpretation of this is it's like the number. And again, you can make sense of these interpretations operationally if you think about like repeated processes where you're transmitting information between Alice and Bob. But let me just say this English language phrase. It's the number of bits of information that Bob learns about x upon seeing y. Now that's funny because it's this is obviously a symmetric between Alice and Bob. This phrase is not symmetric between Alice and Bob, but therefore you can tell that it's also equal to the number of bits of information Alice learns about y upon seeing x. And again, you can kind of tell that story here, like y is at 1. Like Bob gets his number, 1, 2, 3, or 4. And once he gets it, what does he know about x? He basically knows that x has the same parity as the number y that he got. So he got like 1 bit of information about x. And this is also, you know, on average and so forth. And this is also Bob knows the whole joint distribution, like how much information he gets knowing the joint distribution. OK. So now I want to write down some facts and properties about mutual information. Actually, I want to go back a little bit to here. I want to write down one fact about just entropy. And I'll call this an obvious fact. I want to put a star around this. This fact just about entropy is that the entropy of, let's say, PA, the marginal of the joint distribution P on A, is at most the entropy of P. Yeah, I think that's kind of obvious because, I mean, to generate just A, one like potentially wasteful thing you could do is generate the joint distribution of x and y and then just throw away y and generate this. OK, and also, of course, symmetrically, the most entropy you can have in Bob's y is at most the entropy that is in jointly in x and y. OK. And actually, these two facts give us an upper bound on mutual information always. So here's one fact. First of all, the mutual information of P is, or X and Y, is always at most the entropy of just Y. There's a few ways to see it. I mean, if you look at the formula for mutual information, it's this. And the fact that I wrote down just says that like this stuff together is negative, which is equivalent to star. Okay. An intuitive way to see this is also like this is the total amount of information in a draw from Y. And if you think of this as the amount of information about Y that Alice can learn, that's the converse of this, about Y upon seeing X, the most she could learn is like all the information that's in Y. Or another way, if you think about this other interpretation, well, in terms of the savings, if you're trying to jointly generate X and Y and ask how much savings does that give you over generating them separately, the most you could save is everything in terms of saving on generating Y, which is this amount. Okay. So that's a generic upper bound. So whichever of those is smaller is a good upper bound. And well, this is another simple thing. A lower bound is 0. I mean, I guess if you look at this at first, it's not immediately clear that it's greater than or equal to 0. And I mean, that's equivalent to saying that the entropy of P is at most the sum of the entropies of X and Y. And that's sort of like saying the least that you can save is nothing. OK, these are all, I mean, if you don't like these word-based proofs, you can prove all these things by like plugging in the definition with like PIs and logs and so forth. But yeah.
But I guess you can just say that it means that we can always generate the joint distribution by first generating A and generating B and throw X and Y and throw away the undesirable results. And that always works.
Yeah, there should be an interpretation like that. Good. OK, and now I want to tell you one more fact, which again I won't prove, but it's very believable based on these explanations, and you can prove it by making these intuitions rigorous and or by, plugging in the logs and so forth. It's this. Let's say, actually, let me just give one more like example that is instructive. I'll give it in words. First of all, when do you have equality here? When is the mutual information 0?
Independent.
Right. Yeah. This is equality if they're independent. And then this one's a little trickier. When is the mutual information equal to the minimum of these two?
When the second one can be determined.
Exactly. When the second one of them can be fully determined by the other one. Exactly. So the two opposite polar examples to keep in your mind, or good two opposite examples to keep in your mind is, let's say X is always uniform between 1 and D. And then two possibilities. One is that Y is uniform and independent of X. In that case, the mutual information is 0. The other case is when Y is just always equal to X. In that case, the mutual information is like full log D. So good to keep in mind. And now here's the last fact that I want to mention about mutual information. Let's say Alice and Bob are like spatially separated, as we like to have them, Mars and Jupiter. But anyway, they like secretly got it, their draw. Alice gets X, Bob gets Y. And then Bob, think of Bob as like any kind of randomized algorithm that like takes Y and, based on it, prepares a new random variable we'll call Z. And Bob can discard Y and make a completely new random variable Z. He can kind of like lump together some outcomes of Y and like form Z as some function of Y. He can do anything he wants, including using the randomness of Y. But he never communicates with Alice. Then it's a fact, if you really want to get mathy, like z is derived by applying like a stochastic transformation to y. Then what I want to say is the mutual information between x and z is at most the mutual information between x and y. Which is to say, Bob cannot create more mutual information between his random variable and Alice's random variable just by doing local operations. It's quite intuitive if you think about it this way. Like Bob cannot suddenly learn more information about x from y by just like locally doing some stuff and having no communication with Alice. Okay, but this is like an important thing to remember. You know, in particular, for example, if x and y are independent random variables, so the mutual information is 0, like there's nothing Bob can do to create a z that somehow is no longer independent of x. I mean, there's nothing he can do. Okay, and so these are all, you know, kind of important facts to remember about mutual information. Any questions about this rapid fire information theory discussion? Okay, so now we're going to do the quantum version of this, which kind of gets interesting. Like now it sort of gets very interesting, the quantum case. I should mention, like, by the way, that quantum information theory is like a very exciting topic. I mean, lots of interesting open research going on right now. It's also a huge topic. I mean, there's several, like, you know, complete books about it. There's a very nice book by John Matrices from 2015. Just, you know, Google quantum information theory book, and you'll find several good examples. Okay, so let's do the quantum case of mutual information. And there's like a surprise. So what is this? Well, let's start by an example. Let's go to our favorite example for, you know, joint states in the quantum case, Alice and Bob sharing an Epr pair. Okay, so let me write rho for the density matrix, the 4x4 density matrix of this Epr pair. So what is the quantum entropy of rho? I know you can do it.
We computed that already, right?
Yes. And it was?
That was 1.
No. It's the same as the quiz.
Oh,
0. Why?
Pure state.
It's a pure state. Epr pair is a pure state. Its quantum entropy is 0. Okay. Now what is rho sub A? Not this entropy, just what is it? What's Alice's state?
1/2 times I.
That's right, it's the maximally mixed state. Maximally mixed qubit, which is 1/2 times the identity matrix. Okay, and what's the entropy, the von Neumann entropy of that?
That's 1.
That's 1. And that's the surprise. Right, because look at star. Star fails, okay? The von Neumann entropy of the whole mixed state is 0, but the entropy of one of the pieces is more than 0. It's very disturbing. Okay? So this is also, of course, H of rho B. Okay, this is disturbing, but, well, hey, it's a brave new world. It's quantum. It's not going to be exactly the same. Quantum information theory has got lots of surprises, or some surprises. So that's spooky. We don't have this star. Well, I mean, I don't use the word spooky lightly. It's due to entanglement. Okay, the reason this happens at some level is because the Epr pair is an entangled pure state. And in fact, I'm going to, you know, go on and like define quantum mutual information. Actually, I can do it right now. Quantum mutual information of rho, denoted like this. I won't denote it like this. It's this quantity. Okay. We'll study it in a second, but let me go back to this like disturbing situation for a second. So actually, this phenomenon, this failure of this star here, of this pleasant fact, is the right way to quantify the entanglement of a pure state. So I said all those words kind of carefully. So let's say an Epr pair is a pure state, and the two parts are entangled. Okay, but now we can talk about how entangled they are. So this is kind of an aside from what we've been talking about, but let psi be a pure, I'll write it like this, bipartite state. Okay, bipartite state just means, if it's a bunch of qubits, Alice has some half of them and Bob has some half of them, or if it's like two-particle system, Alice has one particle, Bob has the other. And OK, let's write rho for the associated density matrix. So it's a fact. This is not hard to prove that maybe you can guess under what circumstance is the entropy of Alice's part 0.
When another entangled?
Yes, that's right. So this happens if and only if rho A is a pure state. So like there's no uncertainty about A. And if you think about like, if you have a bipartite pure state, it looks like, I don't know, sum of alpha I, j, I, tensor j. You get a pure state, you get 100% outcome on Alice's side, if and only if it's a product state. Okay, so this is if and only if psi is like a pure tensor, it's a product state. In other words, they're not entangled. OK. So not entangled means that. Here's another fact. This one takes some proof. It takes, 10 minutes of linear algebra to prove it, which I won't do it. But it's basically follows almost immediately from a little bit of theory of singular value decomposition. It's this. If you have any pure bipartite state psi, and you look at the mixed state on Alice's side and the mixed state on Bob's side, it's a fact they have the same eigenvalues. It's not super obvious. In fact, well, let me leave it at that. It's not super obvious, but it's true. And therefore, they have the same entropy, because the entropy is only a function of the eigenvalues. OK? And so if you have psi a pure state, then the entropy of Alice's side, is a number. And it's the same as this, so it's symmetric. And so this common number is the entanglement measurement of this bipartite state psi. And it has various nice properties. It's a very enjoyable quantity. It's like sort of the one and only right choice for like numerically measuring or declaring how entangled the two halves of psi are. For example, it's 0 if it's a product state, and like the Epr pair, these are both like a coin flip, so it's one bit of entanglement. So that's a nice use of von Neumann entropy. I should add that people are very interested in getting a similarly pleasant definition of entanglement measurement, like a quantification of entanglement, when you don't start with a pure state, but you start with a mixed state. You can have that too. And it's basically like an open research question to get like a good definition here. There are like many, many candidate definitions of like how to measure how entangled a given mixed state is. They all have various properties, or like it's unknown if they satisfy various properties. And yeah, people don't have like a great theory of how entangled mixed states are yet. So that's something that's worked on. OK. Let me get back to mutual information, though. So in light of the fact this was the classical case, so let me erase this, because like from now on we're going to talk about
Yeah. So it's okay. Like what if I take what if I take two different states, like just some qubits, okay, and they will have a different age, and then I just put these qubits together.
Yep. These are two mixed states.
This will be a pure state, right?
So if you have two pure states, they both have entropy 0. And then if you put them together, there'll be a product state, which will also have entropy 0.
Okay.
Now you could take two mixed states. Yeah, I mean, this is partly why it's tricky. I mean, you could take two mixed states and then stick them next to each other and ask about the entropy of that. And I think it'll be the sum of the entropys.
It's like the fact that if you have a state, and then if you just trace out B or trace out A, you left with the same entropy. Like this is just this annoys me. Like how's that?
Say it again.
So the fact that if you have
it will be
joint bipartite state, and then you trace out B and measure the entropy, or you trace out A and you measure the entropy is the same on both sides. Like
if the starting thing was pure.
If the starting thing was pure, yeah. Like, this is. I don't know.
Yeah, that's funny. It somehow says that like, well, okay. First of all, the fact that this can happen is related to the fact that this can be violated, and somehow it says like something rigid about how this can be violated. Like if this is violated by h of p, the joint state starts, or h of rho starts out at 0. Then we trace out A, you get some entropy on the A side, on the Alice's. If you trace out B, you get some entropy on the Alice's side. Like that has to be exactly matched by like a gain in entropy on Bob's side. Yeah. In fact, this. Let's see if I can get this right. I was not going to mention this fact, but let's see if I can do it from memory. This is a fact. The entropy of a joint state rho is at least the absolute value of the difference between the entropies of the two halves. It's sometimes called the triangle inequality. And I guess maybe it's, I don't know, somehow vaguely related to this. But I mean, you see, it's kind of funny. I mean, if you believe this at all, it proves this, right? Because if the entropy of this is 0, if these guys have non-zero entropy, they better have the same non-zero entropy. Yeah.
So the second fact is only if h of rho is 0?
Yeah. Yeah. OK, let me erase this because I don't want this. See, this is now like a false. I mean, OK, it's got p's, so you can tell it's classical and therefore true. But this thing is disturbingly no longer true. But let me put up some potentially true facts, and we'll then decide if they're true or not. OK, so one thing you might ask about is it true that the entropy of a joint state is at most the sum of the entropies of the kind of two halves? And the answer is yes. This one's true. And it's not too hard to prove. And I can even sort of prove it to you in words. So remember, we had this interpretation of H rho as, like, you can pick your favorite orthonormal basis to measure rho in, the big state, and then you pay, like, how many classical coins would you need to generate the measurement outcomes? Well, one thing you could do if you weren't so smart about picking your favorite is you could just, like, first pick your favorite measurement and cheapest measurement for measuring Alice's half, do that measurement, pay, like, this many bits, and then that actually does not change rho b. If you just measure Alice's side, it does not change the state rho b, because it's something like locally you've only done to Alice's side. So then you could sort of finish the full measurement by, like, picking your favorite measurement basis for this one, the cheapest one for this one, and simulating it. So this would give you a way to, like, measure the whole thing in an orthonormal basis, and you'd pay this much. Okay, so that has to be an upper bound on what you'd get if you picked, like, the overall global best basis. Yep?
Can you also think about it as if this were false, you would have, like, negative mutual information?
Yes, that's right. So in particular, this being true implies that the quantum mutual information is always non-negative. But it's not clear that that should make this true. Like, it's not, now that you have this disturbing fact that the entropy of a part can be smaller of the entropy of the whole, sorry, can be larger than the entropy of the whole, it feels like all bets are off, man. Like, maybe mutual information could be negative. Like, I don't know. It turns out that no, actually it can't be negative, which is actually reassuring. And that's a corollary of this true fact, which you can also, it's not that hard to prove just directly using linear algebra. Okay, so that's somewhat reassuring, at least. So this mutual information is non-negative. And in fact, you can also show it's with equality. Again, this also takes proof. This has equality, or the mutual information is 0 if and only if rho is a product state. Okay, so that's a fact, which I'll assert. Okay, so you're like, all right, that's good. Now, what about this one? This one we got. Thank goodness. What about this one? Do we have this? Is it true that mutual information between two halves is bounded by, I don't know, the mutual, or the entropy, the von Neumann entropy of one part? What do you think about that?
That directly follows from the fact that star is wrong, so this should be wrong as well.
Right. The fact that this is wrong, and it directly follows from the fact that star is wrong. Okay, so this is not true. In general, for example, I mean, we can even see an example with the Epr pair. With the Epr pair, hopefully we'll get this right. What is the mutual information in an Epr pair? Well, the entropy of Alice's half is 1, because it's the maximally mixed state. The entropy of Bob's half is 1, it's the maximally mixed state. The entropy of the joint state is 0, because it's a pure state. So the mutual information of an Epr pair is 2. But these are both 1. And 2 is not at most 1. So, yeah.
Can you interpret this too as a mutual information between rho A and rho B?
This too? I don't currently have a good story on that, no. Yeah. I mean, the best thing you could say is, like, we have some kind of interpretation of these quantities in terms of savings. If you, like, picked your favorite orthonormal basis in each of the cases, measured it in it, and paid classically for generating it. But it comes from just, you know, the fact that, you know, the eigenvectors of a joint state are not necessarily the tensor products of the eigenvectors of, like, the components. So, yeah. So it's hard to, I don't really know, like, a great story on this quantity. Yeah?
Does this somehow represent that, say, if Alice measures her qubits, then she has 2 bits of information about what Bob has?
I'm afraid not. I don't think so.
Oh, say it again. If Alice measures her qubit,
then
She actually knows the box qubit, right?
yeah, which is 2 bits of information.
What?
Wait, how's a qubit 2 bits?
The 2 qubits, right?
Hmm?
Oh wait, Alice only has. Whoops, never mind.
Yeah, in this story, Alice and Bob each have 1 qubit. Yeah. Yeah, so it's a little unclear. Like, I think in part, like, this quantity was defined just because they were like, well, I mean, it's well defined in the classical world. Let's just like define it in the quantum world, and like maybe it'll be useful. And it's like some of the facts are true about it, and some are false. And so sometimes you can use it to like prove stuff. Sometimes you can't. But I will like tell you like one fact, Halevos bound at the end of this, which involves quantum mutual information and is a fact. So somewhat justifies its existence. Okay, so we're batting, I don't know, 333, or yeah, in terms of how many analogs are true or false. Let's talk about this one. So let me just try to modify this. So now maybe you have like a joint state of 2 particles. Let's say entangled qubits or entangled qubits. And Alice is holding 1 particle and Bob's holding another particle. And let's say now, okay, now Bob doesn't have a random variable. He has a quantum state. So Bob's holding some qubit in state rho B. And say he does some local operations, quantum operations. So there's this particle, he's hanging out on Jupiter. Maybe he adds some new qubits in the state 0. Maybe he does like a giant unitary transformation on his original qubits that were entangled with Alice's and these new qubits. Maybe he does a partial measurement, so it collapses his state to some other thing. So, the picture originally is like, here's rho A. It's like entangled potentially with rho B. This whole thing is in state rho. Now Bob over here on Jupiter does some kind of operation, which we'll call phi, and gets like a new particle in state phi of rho B, which may still be like partially entangled with A and so forth. We can ask the same question. Could Bob have increased, by doing these local operations, the quantum mutual information between his final particle and Alice's particle? On one hand, based on the name mutual information, you would like to say no. But on the other hand, like, we don't have the greatest interpretation of this. And some things that we thought should be true turned out to be false. So you might say, who knows? But it turns out this one is true. It's true that the quantum mutual information between Alice's particle and the thing that Bob gets after he does whatever local quantum operations he wants on his particle, it is at most the quantum mutual information between the original pair. So this turns out to be a fact. And I'll put like a little exclamation mark after it. Because unlike every other fact that I've told you so far in this lecture, just one sec, this one is super hard to prove, yet true. Yeah?
Can you also say something about not being able to increase the entanglement measure with local operations?
If they start out with a pure state? Yeah. I mean, it basically follows, right? Well, it's hard to say because, okay, what is the entanglement measure? I mean, by definition, they start out with this pure state, and you view them separately as mixed states. And then this is a fact that these 2 entropys have the same value. And you just say whatever that common number is, that's their entanglement measure. Now, if you somehow then Bob takes his particle and does some stuff to it, then their joint state of their 2 particles may no longer be pure. And therefore, this definition no longer applies. And so you cannot directly say anything. Now this gets actually to one thing I said, which is that like many people trying to define notions of entanglement, quantify entanglement between particles when the joint state is originally pure, or joint state is originally mixed. And I wonder what that is. well, any old way. It's over now. And what you said is like one criterion that they like to have. They're like, man, if I define like a notion of entanglement between two particles, it'd be really great if it had this property that like if you have two particles with a certain amount of entanglement according to your definition, and then Bob does some like local operations on his particle, it should not increase the entanglement between these two particles. And so I think like most proposals for like a way to quantify entanglement of mixed states, this is like a property that you really ought to have. Otherwise, they don't want to call it an entanglement measure. In fact, I think it's generally regarded as like the one property that like if you don't have this property, like you're not allowed to call it an entanglement measurement. Yeah. So yeah, this fact is very important in quantum information theory. It's equivalent to, it's very simply equivalent to a slightly different fact, which is called strong subadditivity of von Neumann entropy. Which if you like look it up in a book, they'll often refer to this, and it's like some inequality involving like, there's like 3 registers and like 2 H's on both sides of the inequality. But it's really trivially equivalent to this. So like I prefer to just remember this. I mean, this is a little bit cheating because this itself, right, has like 3 H's in its definition. But somehow it's easier to remember. And yeah, this was like conjectured by different groups in the 60s. And it was finally proven in 1973 by Elliot Lieb and Mary Beth Ruskay. And it's hard. I mean, it's not like insanely hard, but like I guess it would take like 2 lectures or something to prove it. So it's kind of like a cornerstone fundamental result in quantum information theory that like, at least this one is true. OK, good. So the last thing I'll do is just tell you one more theorem in quantum information theory called Holevo's theorem, or Holevo's bound. It's also proved by Holevo in 1973. It follows very easily, like exercise level easiness, from this fact. But I guess Holevo proved it independently or slightly before this fact was proved. But now, like the easiest way to prove it is just first prove or accept this strong subadditivity and then derive Holevo as a pretty easy consequence. And Holevo's bound has like a nice meaning in terms of communication. So let me tell you about Holevo's bound, Holevo's theorem. And it's related to the thing that classical mutual information is related to, communication between Alice and Bob, like how much Bob can learn from Alice by sending correlated random variable. So let's talk about the classical communication setting here. Let's say P is a classical, I should really call it P sub A, but I'm just going to call it P, classical probability distribution. And instead of having it be on the numbers 1 through D, let me just have it on strings, on Boolean strings. And we're going to have 2 parties here, Alice and Bob. And you're going to imagine that like Alice gets a draw X from P. So she gets like a random chunk of information drawn from P. And then she kind of wants to convey this to Bob. So the way she's allowed to do it is by transmitting another string Y to Bob. So based on the X that she sees, she's going to form some string Y, which is a function of the X that she sees, and transmit it to Bob. And so Bob only gets Y. But Bob also knows P. He knows the distribution on Alice's information or Alice's message. And he wants to learn about X. What Alice's X was, and he knows P. Yeah. Or you can think of, I always like to think in information theory like there's 2 usual applications like communication and like compression. But like compression is just like communicating with a future version of yourself. You know, like you want to like write a message to your future self that your future self can like decompress into your original message. So we'll stick with the communication viewpoint. And this is kind of like what, you know, mutual information is all about. So classically, if you want to ask like, how much can Bob learn? Well, Bob learns at most, you know, mutual information of x and y bits about x on average. Okay, this is like one of our interpretations of mutual information. It's not Bo, it's Bob. Okay, and in particular, therefore, if y is limited to be at most b bits long, like if there's some kind of like external physical thing that's like preventing Alice from transmitting messages at more than b bits, then this mutual information, we know it's always at most the entropy of the random variable y, which, since this is b bits long, is at most log of 2 to the b, in other words, b. Okay, and this just conforms very well to our intuition that if, you know, Alice has some x, she's trying to transmit information about it to Bob, and she can only send b bits, then Bob can learn like at most b bits about x. Okay, so now, you know, in the 60s and 70s and so forth, people are like, hey, what about quantum? What if Alice could send quantum states to Bob? Or if she's compressing, what if she could try to compress her classical information into a quantum state? And now I should emphasize that this question is kind of like a half classical, half quantum question. Because we're imagining still this. Alice has like some random variable x, which she's classical information x she's trying to convey to Bob. Bob is trying to, you know, get classical information out of it. But just the mechanism is that Alice can maybe send some quantum states to Bob. Okay, so now instead of Alice will send states, mixed states, sigma x to Bob. Okay, for every string x that she gets, she can create a different quantum state, sigma x, and send that to Bob. And, you know, Halevo is bound to asking, you know, well, can, you know, you transmit information, classical information, more effectively in this way, or more efficiently? So let's think about some things. So let's look at Alice's. So in this problem, even though Alice gets classical information, you can think of, you know, classical is just a subcase of quantum. So you can think of Alice, her information as a quantum state. And it's rho sub a. It's a mixed state, sum over all strings x of the probability px of that string times just like the classical pure state ket x. That's a quantum way to write like the classical mixed, you know, state of a string that she has. And then when she sees x, she attaches the mixed state sigma x on seeing x. And so that adds, overall to the whole of the story, some more qubits. And so therefore, like the joint mixed state is this rho sum over x of px, that's a real number, x tensored with sigma x. Okay, this is a bipartite state where like this is sort of the classical information that Alice holds, and this basically is given to Bob. So like this is sort of effectively Bob's part of the state. Okay. And now you can ask, what is the quantum state of what Bob has? And it's not hard to check. I mean, it's kind of easy to see that Bob's state, well, he has a pretty simple mixed state. It's just, you know, with probability p sub x, he gets sigma x. So, Bob's state, which is what you get if you trace out the Alice part of this, is this. Sum over x, px, sigma x. And now we're still trying to understand how much classical information Bob can get about x from this mixed state he has. And again, classical information is, it's a special case of quantum information, and therefore you can apply this fact. So this strong subadditivity, this very important fact, implies that no matter how Bob measures, he can add more qubits, he can do unitaries to his sigma, he can eventually partially measure or fully measure and thereby derive some classical information. Whatever classical information he derives, you can bound, I'm skipping a little bit here, but you can bound the information, the classical information of x and y, and this is like, any classical info Bob can get. It's at most the original quantum mutual information between row A and row B. Okay, so the strong subadditivity implies this. Now we can ask the same question. We could say, what if Alice is limited to sending B qubits? In other words, all the sigma x's that she sends over have to be at most B qubits. Now before we said that classically, we had this. And therefore, this is at most, log of 2 to the b. That's the dimension of a b qubit state, which is b. But this is exactly the thing which may fail due to the disturbing situation. So it seems that we cannot make this deduction, although we'd like to. But it turns out this is true, and this is sort of one thing that Halevo proved. In this particular case, this is not the most general possible mixed state. It's kind of like a half classical, half quantum state. And by virtue of that, you can prove, and it's like, like a page, it's like an exercise, it's not too hard, that this actually holds. And in fact, you can just calculate, I won't do it, but you can calculate an upper bound of this, the von Neumann entropy of B, minus this. So it's upper bounded by even the entropy of B minus something. And this whole quantity is called Halevo's chi. Anyway, it's some number. But let's say the main punchline is this all holds, and therefore the most classical information that Bob can get about x when Alice is allowed to send b qubits to Bob is still b bits of classical information. And that's kind of like the philosophical punchline, that if you're taking classical information and try to pack it into qubits in such a way that that information can be reliably extracted, even though qubits seem much more complicated than bits, they have all the amplitudes and so forth, you can still pack at most b bits of classical information into a b qubit state. OK, so I'll see you next.